Okay, good morning. I am Pietro Miele from University of Naples Federico II, Department of Earth Sciences. And here I'll show you an example, an application on monitoring of flood events propagation using satellite data. Every year, flood events cause great economic losses and victims all around the world. Concerning the riverine flooding, the World Resource Institute estimates that by 2030, more than 100 million people will be affected by this phenomena, with billions of economic damages. In Italy, the ISPRA Institute periodically releases hydraulic hazard and risk maps defining three main scenarios. Low hazard class that cover an area equal to almost 11% of the national territory. The medium class that covering an area of 8%, and high hazard class equal to 4%. And as shown in the graph below, 2 million people residing in the higher hydraulic hazard class. So for these reasons, precise flood mapping and modeling are essential for flood hazard assessment, damage estimation, and sustainable urban planning. And in recent years, the increased availability of free of charge satellite data has allowed the study of many natural and man-made processes. Mapping of water surface, for instance, is based on different backscatter regimes of water surface and land surface. And the backscattering mechanism for each pixel of the acquired image determines the type of reflector. In the radar images over the smooth water surfaces, the signal gets reflected away from the sensor, causing low backscattering returns and amplitude differences. In the multispectral products, the water reflects only in the range of the visible spectrum. In the early October 2020, heavy rainfalls in the Alpine region have caused severe floods that hit in particular the Piedmont Italian region. And these very heavy phenomena have caused a rapid increase in hydrometric levels of the various rivers draining the Alpine basins and subsequently flowing into the Po River. Some rivers, such as the Tanaro and Sesia, have broken their banks, causing floodings and serious damage to the infrastructures in the area. So we present a multi-sensor and low-cost approach for flood inundation mapping. And to detect flooded areas, we used Sentinel-1 products combining an image acquired during the flood with an image acquired before the inundation to distinguish between flooded areas and permanent water bodies. In addition, Sentinel-2 multispectral images were considered to obtain the normalized difference vegetation index and the normalized difference water index to analyze the flood's effects on the soil. Also, hydrological data have been collected, and the graph shows how the co-flood image acquired on 3rd of October 2020 was acquired when the upstream station were recording the maximum hydrometric levels. This flowchart explains the adopted procedure. Level 1 ground range detected products consist of focused SAR data that have been multi-looked and projected to ground range. And in these products, the phase information is lost, and there is only the amplitude information. The resulting products have a spatial resolution of about 10 meters with the reduced speckle effect. With the SNAP software powered by ESA, for each Sentinel-1 image, a subset of the area of interest was obtained. And then the radiometric calibration was applied to compare the two images in terms of signal note backscatter. Finally, we applied the terrain correction to combine the two images and to create an RGB composite image. On the other side, Sentinel-2 products were used to obtain NDVI and NDWI indexes with the Sentinel playground environment. And these two combined outcomes were improved and refined by using support data as official documents, technical reports, and aerial photos. And finally, the validated flooded maps were compared with the hydraulic hazard maps. Here we can see the two Sentinel-1 images, and both images were acquired in the ascending geometry with the same incidence angle, very important for the change detection. And the single images were staked to obtain the RGB composite image, where the red channel corresponds to pre-flood image, while the green and blue channel corresponds to the image acquired before, during the event. And we can see that permanent water bodies appear very dark, while the flooded areas appear in red, because over the flooded areas, we have a high backscatter in the archive images, but a low backscatter in the co-flood images. And cyan pixel represents areas not completely submerged, but with high water content. Concerning the multispectral data for the co-flood image, the NDWI outcomes show values greater than 0 in that area. However, they are not the typical NDWI values for water bodies that are about 0.8. And it can be explained taking into account the high turbidity and the high sediment content that is related to the geological setting of the upper part of the watershed basin, where very erodible glacial deposit outcrops. In fact, in the pre-flood image and in post-flood image, the Sesia, the Po and also the Ticino River can be distinguished by typical water bodies value. The same consideration can be adopted for the NDVI index, where the water bodies are characterized by values near to -1, and usually they appear very black. But in the co-flood image, in the area surrounding the Sesia, we can see values ranging from -0.1 to -0.5. And finally, to define the flooded areas, empirical thresholds were adopted. So for instance, for NDWI, we consider only that pixel with values greater than 0.75, obtaining an area about 97 square kilometers. And for the NDVI, only pixel with values greater than 0.85 were considered to have obtaining an area equal to 90 square kilometers. The figure here on the right show the official hydraulic hazard maps according to ISPRA 2018, and we can see that the lower part, the final part of the SAR River, about
Sorry, Pietro, you have 2 minutes.
Yes, thanks. About 35 square kilometers is not included, but in our study we showed that this area has been affected by several flooding events. And in conclusion, this study shows a simple and rapid application for flood mapping with no free of charge satellite data. And the most important data is the co-flood image, if available. And the combined use of SAR images and multispectral products is the best combination to refine and also to validate the obtained outcomes. And also ancillary data like photos, technical reports, and other data can be employed. The features are depending on temporal and spatial resolution of the satellite platforms. And in fact, small inundated areas cannot be mapped with Sentinel products, and also riverine floods with a very short co-flood time might not be detected by satellite platform with revisiting period equal or higher than 6 days. And finally, this analysis could be used to update the official maps of hydraulic hazard, and if possible, in presence of the satellite platform with high frequency and pass and high spatial resolution, this procedure can be used for flood forecasting and risk assessment. Thanks.